All right, so we're recording. And so welcome to the Austin Python Meetup, our 6th Meetup for this year. Yeah, thank you everyone for coming, everyone from Austin and from around the world. Today we have two great talks. Hopefully, Massimiliano and Vinesh will show up, but so far we plan for two talks. And the first talk will be about AIQC, a framework for rapid and reproducible deep learning for open science. And the second talk will be about Meetup, an AI-assisted tool for debugging Python code. And our presenters today are Layne Sadler. He is an autodidact at heart. Layne began on the business side of technology, but curiosity drew him toward building applications and algorithms alike. This led to co-founding an API-driven startup called Athlete.studio. And he's spearheaded product development at a biotech company called Genuity Science, while working at pharma and research institutes on national genomic biobank projects. He observed barriers that prevented the adoption of deep learning in scientific research, and gaps in machine learning tools. So he built the AIQC to address those problems. So he's going to do that talk today about that. Our next speakers, hopefully they will show up today, but next speakers for the second talk, there are going to be two speakers for the second talk, is Massimiliano Genta and Vinesh Gopal. So with that, Layne, the floor is yours.
All right, thank you so much for the intro and for hosting. Not everyone's doing the meetups until everyone's back in person, so it's great to see you guys continuing to keep the community going strong. So I'm going to go ahead and share screen. Just real quick, people always ask, is the code on GitHub? And yes, it is. So if you go to github.com/AIQC, you can find our source code, and the documentation is all in here. And there's lots of great workflows already in here for either installing, getting started with example data that's built into the package, and then going to town on classification and regression with PyTorch and Keras and TensorFlow. More to come. And a bit of housekeeping. So we'll talk a little bit about the origin story. We already kind of covered it in the bio, and then we'll do an overview of the framework. We'll jump into a demo of our latest feature, which is heterogeneous or mixed multimodal data analysis, where you can use data from different types in the same analysis. And then we'll jump into some of the really nitty-gritty pre-processing challenges that this library shines at addressing. So as I mentioned, I spent the past 4 years working with Big Pharma on national biobanks, analyzing 500,000 samples for a population like the UK, or 2,000 to 4,000 samples for a rare disease. And I kept waiting for the dino DNA. Sadly, it didn't really happen for me in Jurassic Park. But at the same time, I kept waiting for someone to jump in and say, now's when we start the machine learning. And when you're working with thousands of samples, you're looking at something like DNA that has 5 billions of nucleotides, and merging that together with medical records in a longitudinal analysis, I just didn't feel like an association study was good enough. So I kind of sought to understand why machine learning wasn't being used for people that really had the budgets and means to handle it. And when you start to dig into it, writing the logic of a single machine learning algorithm and evaluating it. It's not that hard. You do have to write some code to stitch it together. But then when you look at the pre-processing and all the data challenges in preparing all the different data types that I described for analysis, there's a lot of more code that you have to write. And the result is you've got people that are doctors, biologists, and scientists, and they're not necessarily the world's best programmers, and they're faced with these really pressing questions. And in comparison to some of the rigorous scientific protocols that are out there, such as genomic variant calling, it's very structured, very well defined. Machine learning workflows from data type to data type and analysis type. I mean, I haven't even looked up how to do transformers yet. They're really oral histories, and they're scattered in tutorials and repositories. It really creates a programming burden on them. And at the same time, they may not be data science experts. So you've got this skill set trifecta of science, programming, and data science that makes it pretty infeasible. And then, of course, when it comes to research, there's always budgets, and then there's solutions out there for this, but a lot of them are behind walled gardens. So I thought, could I make something that's simple, object-oriented, so it's easy to understand, automated, and free. So here's where we're at. We're talking about an overview of the framework now. So the x-axis that we've got here are the different data types that are supported. So right now it's tabular and image. Today I got most of time series working. One of our contributors is working on text pre-processing. And on the left here, you have the type of analysis. So classification, what is it? Quantification, how much of there is it? And then generating future samples based on existing data. So, we have this top left quadrant here working for both Keras and PyTorch, some TensorFlow examples too, which it's pretty much Keras these days anyways. And it's my hope to fill in the rest of this grid over time. And the framework, stepping through the framework, it starts with pre-processing, right? So you've got different data types, and then what we aim to do is have pointers to the data. So rather than actually splitting and folding the data up and slicing the columns apart and then duplicating the data, we just record pointers so that when it comes time to do the analysis, you say, these are the columns I want to use, these are the sample indexes that I need to call, and you can rapidly pull them into experiments. So it does support hyperparameter tuning. It allows you to tune not only your parameters, but also your topology. So you can play with the network, you can play with different loss functions and things like that too. And we'll take a look at that in the demo. And then from there, this is all on your local machine. So you say, these are the experiments that I want to run, and then it's going to queue those up and start executing them. And then what seems to be people's favorite part is that it's automatically going to calculate metrics and charts based on the type of analysis that you are conducting for every single split and or fold that you have specified. So it really just takes a lot of the manual scripting out of that process. And recently we added support for doing the same on inference. So when you show up with new samples that weren't in your original training set, you can apply the same preprocessors to them, and it'll generate the metrics for you. It's entirely reproducible because this is essentially an ORM for SQLite for deep learning, right? So there's a SQLite file that gets created when you essentially import the package, and then every decision that you make is recorded along the way. It itself is just a pip package, AIQC, that you can install, and it's an object-oriented framework for deep learning. So rather than saying like, X and Y, we have concepts like features and labels, or targets, depending on the kind of analysis you're conducting. All right, so I'll jump into a demo, but if there are any questions, I'm just taking a quick look at the chat. Feel free to interrupt, or I'll just keep carrying on with the demo here.
Let me interrupt you before you go on. You said it's fully reproducible. However, GPU technology itself is such that will not, if you run the same neural network on the GPU, it may not necessarily produce the same result just because of parallelization issues. So it's reproducible to the point of what?
So it's recording how you're pre-processing your data and the parameters that you're using. And the reason why I harp on reproducibility is that a lot of the experiment trackers, they start at the hyperparameter phase. So I'm not talking about, floating point precision. I'm not talking about making neural networks deterministic as opposed to non-deterministic. In fact, it has a repeat count as one of the settings that allows you to run the exact same combination of topology, parameters, and pre-processing steps multiple times, just because of the fact that it is inherently non-deterministic.
Thank you. You gave the correct answer. Thank you.
Any other questions before I keep carrying on?
Yeah, so you might be getting to this later, but I was curious how customizable the different parts of that workflow are. So for example, if your sort of stratified splitting wasn't as flexible as somebody else needed, how easy is it to write your own custom train test splitter?
At the moment, it's not. What I want to do is I want to draw a line and say you can use your own pre-processing, you can show up with your own arrays, or you can use ours. But at the moment, you're pretty much stuck with what's in there. Let me pull up that specific section of the code. Here are just some of the basics, right? So like if it handles validation splits, you can also do something called a bin count because it handles stratification for you. But yeah, it's meant to make the 90%, handle 90% of the use cases pretty much automatically. So it's not necessarily meant for a data scientist. It's meant for someone who deep learning otherwise would not be approachable. So it provides a workflow. You can go into the source code and make a pull request, but you're kind of stuck with what you got. But if you have suggestions, I'd love to make it more customizable because it would just be just another parameter that we would add here.
Mm-hmm.
Okay.
Thank you so much for the answer.
Yeah, and feel free to ask more questions too.
Does it interact with a compute cluster for big problems, or is it more smaller problems that you'd run on a single machine?
So vertical scale would be your current solution for scale. Looking forward, I need to evaluate solutions like Ray for just the promise of distributed Python code, or running one container per job. Your training jobs, there's a concept of a job, and one of those would go to a container. So no, it doesn't do that at the moment, but it's going to have to, because I'm entering into university astronomy collaborations where they have gigs and gigs of data for a single run. So looking forward, yes. All right, so I'm going to go ahead and import the package and make a fresh database. So initially when you set up the package, all you have to do is AIQC.setup, and then what that's going to do is within a local folder in application support or appders, it's OS agnostic. It's going to create a SQLite file that is going to host your experiment, and from what we're going to do in this example is we're going to classify different galaxies. So I've got this built-in data called galaxies.tsv, and we'll just take a look at that. It's got a link to an image, and then it has some metadata about that galaxy. The target is going to be either a bar or spiral galaxy, and so we're going to use this tabular metadata, and then we're going to work with this image and pull that in as well. So first thing we're going to do is create a data set of type tabular using this data. And for our label, we're going to use that morphology column that we saw above. So we're saying, use this on this data set, make a label. And now we're going to specify a preprocessor for that label. So we're just going to say scikit-learn. We'll use ordinal encoder just because it's binary, 0 and 1, just 2 categories. So we get away easy there. And then we're going to derive features from this. We're going to say you can include or exclude, and we'll say exclude the columns of the label and the the manifest column. And how the feature encoding works, I just kind of drew this up so I could explain it a little bit better. You start with all of your features in a given split or fold, and then you either want to include or exclude them by the name of the column or the type of data, right? And then it allows you to apply different preprocessors to those on the fly, right? So for data type float, I could apply one type of encoder, and then for data type of object, I could apply a different encoder, right? And then if you don't touch them, it's just going to leave those as is, and it's going to concatenate your data at the end of the experiment. And it does this in what's called an encoder set. So here we're going to tie this encoder set to our feature, and we're going to say use StandardScaler on the column of clarity. And it's going to go ahead and attempt that to make sure that it works. And then it's going to say, these are the remaining columns that you haven't encoded yet, right? So now we're going to go ahead and encode the angle using OHE. And it says, great, you've encoded all the columns in your data set. Now we need to prepare the image data set, right? So we have that manifest, right? And this is actually probably going to fail. Oh, no, it worked. Okay, all right. I didn't know what folder I was in, so I was looking at that. So it allows you to specify a folder of images and pulls those in. And then since I have that loaded, we use Pillow to talk to the image data sets. So each data set type is handled a bit differently, and we'll just pull up some examples of that. Here's 2 bar galaxies, and then here's 2 spiral galaxies that we have ingested, and we're going to say let's make a feature from that image data set that we just made, right? So I described the concept of features twice. So when you're splitting up the data, you're going to have a label, your Y and your X's, right? So recently we added support for passing in a list of features, and it knows how to fetch those regardless of their dimensionality. So they could be 1D, 2D, 3D, ND. It just knows how to handle those. And introducing a validation split is as easy as just specifying the number, and it's the same with test, right? So we're going to split this up, and your label is not numeric. I just pushed a bunch of features today, so maybe I broke this, but I did test this before I ran it. Your label is not numeric, either NP floating. Okay, so it's saying that my label is not encoded, right? So did I not include label coder, make label? Okay, label is morphology. Dataset already has a label, great. Okay, let's try this again, but I feel like we're going to be stuck here. Yeah, interesting. Okay, so bin count didn't work. I don't know why that is, but I'll look into that. Anyway, so we have our split set, and what split set does is samples. It makes a dictionary of samples. So here you can see train has these indices in it, and test has these indices in it, and validation has these indices in it. So when I go to fetch data from these features and the label, it just looks at the index and goes and gets it. So it's not really duplicating the data. And it will make it nice for that kind of distributed scenario that we talked about, right? So now we get into defining a model, and this is going to pack an algorithm function, an algorithm object together, and all you really need to do is specify build and train. It will automatically pick loss, optimization, and prediction functions for you, but you can feel free to provide custom ones, right? So this function to build the model, this is the topology, right? So we've got a convolutional tower here, and we've got a tabular tower here, and then they're going to get concatenated together in the end and converging on one one output neuron, right, which is the binary classification. So there's predefined objects that we make accessible, so that like you don't see me passing in arrays to this, right? I'm just kind of calling them, and it's going to hand it to it behind the scenes. Same thing with when you train the model. Again, you can customize things, or you can specify your own hyperparameters. And I kind of glossed over that in the model, but it's nice because you can say things like if this hyperparameter is present, do this entire layer. Okay, so now we're going to pack that into our algorithm object. We've specified these hyperparameters here. It's just going to brute force them. And you can see what I'm testing right now is the number of convolutional neurons. So multiplying it by half or 1 just to see what happens, right? And I'm going to say algorithm, attach these hyperparameters. And then finally, I'm going to make this queue of jobs so that we can run it. And this has a repeat count of 5 on it, which is pretty high. So I'm going to dumb that down to 2. And then we're going to run the job. And this will take a while. So while that runs, I'll show you some of the metrics that we can pull up. There's plots. This is the Boomerang Plot. It's unique to AIQC. It'll show you for every split or fold. On the right, we've got the models, right, that we've trained. And then here we have the results. And we're looking at x-axis, x is loss and accuracy. And you can see this purple model is pretty tight or precise. And you can see train, validation, and test splits all right there. So it's pretty easy to pick which one is the best model or the most consistent. And then down here, it records the hyperparameters for each job. And you have the basic kind of weights and biases charts here. And for classification, you've got all the different classification graphs that one would expect. So you have ROC and confusion matrices. Okay, let's see how we're doing here. All right, so this is done. So we'll take a look at that. And here, just to show you, for every single job, we're calculating all the metrics that you could possibly want. So it's very easy to just run everything under the sun and come in here and pick the best model. All right, and how do we do? All right, these are the ones that we produce. You can see this red one, although on train, it was 90% accurate, and on test, it was 85% accurate. It didn't generalize well because it bonked on the validation. And this green one looks pretty good. It's got a predictor ID of 1, right? This is just an object relational model, so we can come in here and take a look at that specific model. So yeah, it probably could have even done better if we were more patient with the early stopping. And I just want to finish right here by taking a look at that. Right, so again, every split, you've got all the charts and plots that you could possibly want. So yeah, I'll stop presenting there. We can continue to, time dependent, we can talk about some of the pre-processing challenges that it solves. But I'm wondering, did the second speaker arrive?
I don't think so. Massimiliano Vignesh here. I can see the list of people, but I think they might not be here yet. Yeah, I think we can talk. Yeah, if you have more to...
Before you go on, I would like to try to characterize it and correct me if I'm wrong. Your package, in general, what it does, it provides automation for pre-processing and post-processing of machine learning tasks. Am I correct?
Yes. I'd say deep learning specifically, though, because it doesn't do any generic machine learning tasks.
So it automates things that usually people have to program, and you're trying to aim towards people who not necessarily are machine learning programmers, and you're trying to simplify machine learning for them, correct?
Exactly, yes.
So if someone is a complete novice, doesn't know a lot about machine learning, will it be easier for that person to actually access your code and try to do some machine learning with it than try to do some machine learning using, I don't know, Keras or PyTorch? Or should they have knowledge of Keras and PyTorch and then only they can access your library?
At the moment, you still have to know how to write a Keras model. Right, so I'll come in here and pull up the simplest example. You still have to know how to write like the function to train your model. In the future, I'm going to provide defaults for these. But I'd say if you're running a single model on a very simple data set, yeah, just go ahead and use Keras. But if this is something that you know you're going to be doing a lot of, and you need to use things like validation splits, you need to produce the charts to prove that your 99% accurate model is legit, you're going to run into a lot of scenarios in the creation of the metrics. Like the metrics alone vary between regression and classification, and you have to do a lot of scripting to get those right. And then you have to do a lot of scripting to get those right again for plotting. So when you start to dig into the evaluation of the models, that's where this really becomes clear.
Okay, now I'll ask a different. I'm trying to pinpoint something. I know that today many models are like generic. You can find them in like TensorFlow has a hub where you can actually pull the models from, and also ways to actually take existing models and apply them to your data. So if you're using off-the-shelf existing models, and you know how to find them because it's very easy to find by Google search, but if you know how to do this, will it make things machine learning accessible to non-programmers?
To known programmers, you're saying?
No programmers. So people who are non-programmers. Sorry, apologies.
Yeah, I mean, I guess if they're comfortable copying pasting from a predefined workflow in a Jupyter notebook, I would say, the high-level API has 2 steps, right? All those feature and encoding steps that I mentioned, I boiled down into this one pipeline object. I was showing you guys the low-level API, and then that once these functions to build and train the model are automated, which is just, I was waiting for a contributor to do it. I'd say, yeah, a non-programmer could do deep learning, and they would have really good proof of what they're doing.
Okay, now let me be, I'm pushing the envelope here, and you can stop me if I'm pushing too much, but basically what you're telling me is that you're trying to make things, machine learning accessible to public that is not does not currently access it, and if not now, in the future it will be like blocks that you plug in and maybe diagrams or something like this. So basically you are creating a tool that will help people do machine learning if they are not familiar with all the machine learning details. Am I going in the right direction?
Yeah, it would allow doctors to continue to be doctors and biologists to continue to be biologists. And these blocks that you describe could kind of be dragged and dropped on a WYSIWYG GUI that's open source. I've seen technologies that do that are closed source, but
okay. So what you're doing is actually highly valuable. You should find a source of funding and an investor to actually push it forward. There are many uses for it. I urge you to continue and do this. But that's me. And for now, maybe you should continue with the examples. I have enough questions for now.
Thank you. So yeah, if we don't have anything else to discuss, I mean, we could break here, or we could talk quickly about some of the preprocessing challenges.
It sounds like you've got a whole lot of experience in the biomedical with analyzing DNA. What are some of the examples of some pre-processing you would do with some of those biomedical applications?
Yeah, an example there would be imputation is different, right? So for us, imputation is just kind of like looking at the existing data and saying, based on the statistics that we see here, we believe that this feature is, this number, and it could just be a mode or a mean or an average, but that doesn't really cut it in genetics, right? So they have more advanced algorithms for that in pre-processing, and everything is going to be, G, T, C, and A. But they're kind of just using a lot of their own R packages that know how to work with the data intuitively. So encoding, preprocessing, interpolation, imputation are all kind of different from something like scikit-learn and Keras and PyTorch encoding. Yeah, that's just one example.
So you've got all these kind of GNC basis of the genome, but then you kind of break it up into segments, or because it seems like there's a long sequence and I mean I've got a lot of experience with images, but trying to think of how those kind of problems get solved and what are some of the interesting challenges with a number of that DNA data.
Yeah, so every organism is different, right? So you've got different chromosomes, different ploidy, but you mentioned imaging data, right? You have 3 dimensions there between colors in colored images. So for DNA, you've got chromosomes, so you would break it up, 1 to 23, and then mitochondrial chromosomes. And it gets a little weird even there because you've got, double X for female and then XY for male, I think, is how it works. Different chromosomes for different genders. And they're huge. We're talking about, this could be gigabytes of data for one individual. So the chromosomes almost act as a method of parallelization because they're already divided. So each chromosome ends up kind of like going to one machine for pre-processing. That's the start of the journey there.
Oh, so okay. So there's kind of a standard organization based on the chromosomes and in this kind of a hierarchical structure. Interesting problems there.
Mm-hmm. And then within that, you've got genes and introns and exons, coding and non-coding regions. All right, so I'll just talk about this stuff really quickly, why it's important to use a validation split. So let's just go through a thought experiment. Let's say we train our model and we get a 74% on our test split, and then we make some changes based on this, right? And then we see both of our splits go up. We're still not really there with our test split, so we decided to make more changes, and then finally we've got it. And what we've really achieved is bias, because what we've done is say, let's look at the holdout data and see how our model performs on it and make changes based on how it performed on the holdout data. So you've used 100% of your data set to train against, right? So that's why...
Please share your screen.
Oh, I'm not sharing my screen. Goodness me.
Thank you.
Yeah. That would be a little awkward, right? So, yeah, as you can see, we're improving over each iteration on the test split. And that means we've used our entire data set. So that's why it's important to use a validation split as kind of a proxy. It depends on how much data you actually have, but when I started to attempt to do this, I was like, there's no really predefined way to just generate a validation split, which I thought was surprising. And you have to do things like math to do that, and I didn't want to do math every time I wanted to make a validation split. I mean, I did, I wrote it, but you shouldn't have to do that. Another problem is data leakage. So when you're doing your encoding, in tutorials, you'll sometimes see people fit and transform on the whole data set. Like, let's say it's something extremely simple like an average. If you're taking the average of the entire population, that is going to introduce bias because you're supposed to only know about the training splits, right? So this is when you're leaking data in, and it's extremely hard to apply these kind of transformations to splits and folds dynamically on the fly, especially when you're doing something like cross-folded validation, right? So you almost essentially, it's infeasible to do this by hand, and if you do, it's going to take you way more time than it should if you're doing multiple analyses. Right, and then encoding, I discovered, is hard because the x-axis here are the different types of data, either 1D or 2D, integer or float, negative or positive, and a 0 is if the encoder works for it, and a 0 doesn't work and a 1 works. And then here are half of the scikit-learn encoders. There's uppercase and lowercase scikit-learn encoders. So again, doing this dynamically, if you just show up with data and you split it up, it's not just going to work, which is why there's a lot of trial and error. So I had to do some kind of heuristic approaches to fitting data dynamically. And then last is just kind of like my complaint with the industry is, let's stop calling it X and Y. Let's just call it, features and labels. I get them confused every single time. They're like, statistics and things like that. But a lot of the experiment trackers, your data only exists in memory. They count on you showing up with the data, and if you can't answer something that you should be able to tell your 7th grade science teacher, like, I used 70% of the sample, I don't know which ones I used. You should be, like, if you're trying to prove something to the FDA, or proving a scientific experiment, you should know what samples you actually trained on, and that's why recording the entire end-to-end workflow helps when it comes to data lineage. And yeah, that's it. That's the talk in entirety.
Yeah. Now you'll have to explain several things for the newcomers. We have in the Python Meetup, we have people of different levels. You assume you're talking to machine learning engineers. If we still have time and the other speakers are not here, can you explain, and this is Flo and will tell you.
Yeah, I think the other speakers are here. So,
well, stick around. You'll have to explain those things later.
It's okay, guys. If you want to, we can wait 5-10 minutes. No problem.
No, he'll stick around. Stick around till after the talk. Some of the newcomers will ask you those questions. I'm asking it for them because you ran over what cross-validation is. You'll have to explain this concept at all.
Yeah, I'm somewhat familiar with machine learning, but there's a couple of things that I haven't heard before. So I'm not doing machine learning every day. I'm actually just writing Java code. I'm doing a lot more than that. But there's some things that I haven't heard before, so I might ask after. But yeah, are there any other questions for Layne?
Thank you for having me.
Well, thanks so much. It was great. Great talk. Thanks so much.